anybody who doesn't know me, so I don't need to introduce myself. But in the possible case that any of you haven't heard, I am retiring the end of this academic year, and it's in the middle of this coming summer. And you might wonder what's going to become of your language center. And so I may be calling on some of you to discuss that and to make some recommendations, since the dean doesn't seem to be thinking about it.
That's a big news.
Huh?
That's a big news.
Yeah. Well, yes, it is to me anyway.
After all this, you haven't retired.
Well, I thought I'd see it started off in the new site here, yes. Yes. I am having quite a lot of fun this year, but I've been having fun for a long time. That will be my 40th year at Cornell.
Wow.
I was first hired in the summer of 1978. Some of you may be before. So today we have Morten Christiansen as different from many of my past talks. He's a professor of psychology here at Cornell University and director of the cognitive science program. And I thought I'd read very briefly from the cognitive science program website what we do in cognitive science. In the cognitive neuroscience lab at Cornell, we aim to develop a comprehensive account of the evolution, acquisition, and processing of language. You can refer to Christiansen and Chater 2017. Our research is conducted within a unified framework for understanding language across multiple time scales. The time scale of thousands of years over which languages themselves evolve, the time scale of years over which children acquire the language of their community, and the time scale of seconds in which particular utterances are spoken and understood. We approach language using a variety of methods, including neuroimaging, eye tracking, statistical learning experiments, psycholinguistic studies, corpus analyses, and computational modeling, as well as with different subject populations, ranging from infants to adults with and without language impairments. Comprehensive account can be found in another one of Professor Christiansen's books. So I commend you to him to speaking to us today about squeezing through the now or never bottleneck. And you'll find out what he means by that. Chunking in L1 and L2 learning.
Well, thank you. Oh, it's funny having this mic on here. So normally I don't have a mic when I speak in a room this size. Well, thank you very much for inviting me to come here today and speak to you. Now, I haven't been here as long as Dick has. I've been here 16 years here at Cornell, so a little while, but nothing in the same ballpark as Dick here. So, but I have been interested in language for a very long time. Now, I should say here at the outstart that I don't actually do work on second language learning. So let me just get that out of the way first. Now, that doesn't mean that what I'll be talking about may not be relevant, and I hope that maybe we can talk about the ways in which some of the work that I've been doing with my colleagues might be relevant for some of the things that concern you and that concern the Language Research Center. And in particular, some of the ideas that relates to chunking in L1 may also be important for thinking about how to teach and how to measure, for example, proficiency in second languages. So I'm going to start somewhere completely different, though. So in her 1993 book, the philosopher Susan Hack, the book is called Evidence and Inquiry. She used the analogy of a crossword puzzle to illustrate the power of integration across methods and levels of explanation throughout the natural sciences. And it would be lovely if a similar kind of sort of metaphor could be used for what goes on in the language sciences. However, the problem is that in general, when it comes to language sciences, what people have done is, instead of, if we imagine that in order to understand language as a whole, we would need to sort of fill out this crossword puzzle. I imagine, obviously the cues would be a little bit different. But what happens is that the language sciences have become fragmented in a variety of ways, such that people are oftentimes focusing on a very narrow aspects of it. So say just looking at a few cues that go across here, and then people are hoping that, sort of forgetting the rest of the puzzle and hoping that magically everything else would fall into place. If we just know these things across, everything here will come into play automatically. But of course, as anyone who's tried to solve a crossword puzzle knows, that just because you solve the ones going this way, it doesn't mean you necessarily get the cues going the other ways. In fact, oftentimes, looking at the cues at the same time can be incredibly helpful for figuring out how things actually work. And that's sort of the idea behind the metaphor from Susan Hack. Now, unfortunately, what have happened in the language sciences, and in particular in the kind of areas that I have focused a lot of my work on, namely on the acquisition, processing, and evolution of language, questions relating to each of those areas have been treated in isolation from one another, sort of kind of missing the whole point about the interaction across different levels. And what we need to do instead is trying to address how language arises across these different timescales, and that's what we've been trying to do in my lab and in the work I've been doing with a lot of colleagues. And also, I think this actually includes ways of thinking about second language learning, as well as hopefully we can talk about. Now, one of the papers that Dick was referring to before was a paper that came out in July in Nature Human Behavior, in which my longtime collaborator Nick Chater and I argued that what we need to do is integrate across the language sciences in order to work together across different areas and to arrive at a sort of better understanding how language works. And that also includes, I think, thinking about second language learning as well, and ideally perhaps centered within an integrative department of language science. At least that's something I would love to see, where people working on language brought together in one department, independent of the focus of what people are doing. But that's sort of by way of background. What I'm going to talk about today is some work we've been doing trying to work across these different areas, and in particular work related to what Nick Chater and I have called the now and never bottleneck, and that's a key constraint. A key constraint on language that works across multiple timescales, as I'll be talking about. Today I'll focus on language acquisition and processing in particular, and how basic processes of chunking, which is a basic memory process, how that how that kind of process can be understood across multiple timescale. So what I'm going to talk about is first introduce the concept of the now and never bottleneck and what it means, and it's also, I believe, relevant for second language learning, and then how we can think about language acquisition as going through processes of chunking, which I'll explain to you. I'll talk about some computational modeling we've been doing. Then I'm going to talk about how we apply that model to modeling aspects of second language learning, and then also talk about how one of the outcomes of this is the notion of multi-word units, multi-word chunks, as sort of a key building block of language learning and processing, and how we found evidence for that through psychological experimentation. So let me first introduce the now and never bottleneck. Now, oftentimes when it comes to talking about language, rather surprisingly for those of us who perhaps who work more closely with languages, language is often compared with vision. So Chomsky famously have suggested that the faculty of language is more or less on par with the system of mammalian vision, insect navigation, and so on. So the idea is it's like an organ that requires relatively little input in order for it to come into working conditions. So you're probably all familiar with this. Steven Pinker have popularized this in his book, How the Mind Works, where he suggested that we do not learn to have a pancreas, and we do not learn to have a visual system, likewise with language acquisition. So the idea here is that language acquisition sort of unfolds in the brain in the same way that a chicken grows a wing, as Chomsky famously have suggested. However, it's perhaps useful to then actually look at vision and consider what happens if we look closer at perception. Now, when it comes to visual perception, we have this illusion that we have these very rich representation of what's around us. So we like looking around this room, we have this idea that we sort of have these very rich representation of the colors, what's in the room, and so on. But that's actually not true. It's a trick that our mind plays with us, that in fact our visual perception is in most cases very limited. And part of the reason is it doesn't have to, our vision system, our brain doesn't have to represent everything that's in here, because we can always look back. That's sort of the advantage. But our intuitions are that we have these very rich representation. We can see colors out here in the periphery, which you can't actually. It's just that we know what the colors are because we can just look there very quickly. But all sort of experiments have shown that our visual perception is actually much more limited than that. One kind of experiments that have demonstrated this very nicely is studies of what's called change blindness. So here's an example of the flickering in and out sort of simulates moving your eyes when you are doing a saccade. So when you're moving your eyes, you're not actually taking any information in. Only when your eyes are stationary on something will you actually take information in. Now, what happens here is that, especially if you're going out on a plane ride soon, you don't want this to happen, because as perhaps you can see, there's an engine coming in and out of existence here. And people have done loads of experiments like this where something pops in and out of existence, and it can be gradually or sort of very suddenly, like here. And oftentimes it can take a long time for people to discover it, even though you feel you look at the picture and can see everything. Now, so you might be thinking, well, this is just sort of a trick of psychologists, and that, you know, if you're just sitting talking to somebody, then you have this rich representation. But actually, that's not the case either. And this actually was a study done in the psych department here, and you might recognize this is outside Juris Hall. And if you can see here, yeah, so somebody coming up being asked for direction, and then sort of very trickily, that person being exchanged with somebody else. Now, you might be sitting here, it's like, well, okay, I would notice that. But actually, more than 50% of the people that were in this experiment did not notice that somebody else was there. Now, if you exchange a man with a woman and vice versa, then you will discover it. But if it's another man with another man, a woman with another woman, we tend not to notice this. So what this means is that what we extract in terms of visual information is actually surprisingly minimal. Even though we have sort of this intuition of these rich representations. And that's because our sensory memory is actually quite limited, not just for visual information, but also, as I'll talk to you a little bit about shortly, it's also true for auditory information as well. Now, this, of course, is relevant for those of you who are interested in things like sign language and so on, because it matters, these limitations matter here. What happens is that as new input comes in, it quickly will interfere with and override previous representations of information. So if you're not doing something with it, then that information will disappear very, very quickly. So only when you pay particular attention to what's there can you and sort of encode that information, will it stay with you. So that's why we know, of course, we can remember the features in the face of our loved ones and so on. So it's not that we can't remember anything, but we have to process it. We have to sort of put attention to it and process it, and that's important. Now, this is what Nick Chater and I called in our never bottleneck, that if the input is not processed immediately, it'll quickly be subject to interference from new information that'll come in and override it, like in the visual case here. And the way we suggest that our cognitive system deals with this is engage in what's called eager processing. So try to recode information as quickly as possible in order to avoid it being overwritten by the new incoming information. And that unprocessed information essentially would be lost very quickly. Now, in order to have information, some of this, the newly encoded information sort of stay with us for a while, we have to recode it at multiple levels of representation, more and more abstract levels of representation, and each of these levels of representation will buy us more time. And our cognitive system also has to engage in what we call in anticipatory processing. That is, we have to try to predict what comes next, because that way we can more easily encode the incoming information. And the idea is that when it comes to motor behavior, so like moving your hands around like I'm doing now, or other kind of things, we do the same thing in the opposite direction. But what about language? And in particular, what about linguistic input? And here I'm going to ignore sign language for the rest of the talk. The same applies to sign language, but I'm going to focus on spoken language here. Now, one of the things that we have known for a long time is that the auditory trace, the sound that comes into us, stays with us for an incredibly short amount of time. So it's in the order about 1/10 of a second. If you don't do something with it, it's gone. You cannot bring it back. And likewise, when we speak, we actually produce auditory output at an incredibly rapid rate. So on average, a speaker will produce about 10 to 15 phonemes per second. Now that is really fast, because if I was to play to you essentially non-speech sounds at the same rate, at a rate of say 10 sounds per second, you would not be able to distinguish these sounds from one another. It would just sound like a buzz. Yet we're able to, when we listen to speech, to separate these phonemes from one another to a reasonable degree. And again, this is something that we have known for a really long time. And not only is our memory for individual sounds, the auditory trace, incredibly short-lived, and the speech comes at us at a really rapid rate, but we are really not very good at remembering even sequences of sounds. Now, there's some beautiful classic study from 1969 that if I was to play for you just 4 non-speech sounds, so something like a buzz, a hiss, a tone, and another tone, and all you had to remember was the order in which they occurred, you wouldn't be able to do that very easily. I mean, you can of course be trained to do it, but initially that is something that people have a really hard time doing, just 4 sounds. And of course we know that even if it's linguistic items, if it's just a random list of words, we're really bad at recalling that. So on the order of between 4 and 7 words or word combinations. So that's incredibly sort of limited. So this is what our language system has to work with in terms of the input. It has to deal with essentially sound that disappears very quickly, sound that come at us really quickly, and then we're not very good at keeping these things apart or trying to remember them in terms of the sequences. So the question is, how does the language system deal with that? And that's sort of what I'll be talking about today. And in order to give you an idea of how we think this works, I'm going to have you do a little experiment with me here. So I hope you're not too tired here at the end of the day. So the solution we suggest is what's referred to as chunking. And what I'm going to try to give you now is sort of an intuitive idea of how chunking actually works in the language system. So let's do a little experiment. Now, what I'm going to do here now is I'm going to read aloud to you just a list of letters. And when I do this, I just want you to repeat the letters back to me, okay? This is like a very simple memory experiment that, you can do with 3-year-olds. Ready? C, T, A, H, E, P, A, L, C, P, I, A, R. Okay, it's hard. I mean, I just told you that your memory is about 4, right? So, yeah, plus minus 1, right? So this is 13 letters, right? Okay, here they are. Okay, this is hard. I know. I was tricking you, right? But okay, I'm gonna give you a second chance, right? I'm gonna give you a chance to redeem yourself. So are you ready? Same thing again. I'm just gonna read some letters for you. Okay, ready? C A T A P P L E C H A I R. Whoa! You're like a memory magician. What did you do?
I noticed that CAT I could recode into something that I didn't have to remember as 3 different letters.
Exactly. What you just did is chunking, right? So, of course, what we have here is actually the same 13 letters from before, just in a different order. You can see it makes 3 words. And what people will do, if you sort of catch on to that, you'll sort of chunk it into 3 words. So now you only have 3 units to remember. And then you can sort of read them off. You can just spell them. Sorry, but okay. You can just read them back off again, and then that's how you can spell it out aloud. So the theory is that what our language system does is something very similar, but at the level of sounds and other levels of representation, as I'll talk to you about in just a second. Now, importantly, this, of course, is highly dependent on experience with language, right? If you didn't know how to spell cat, apple, and chair, it wouldn't help you at all. If you didn't know English spelling, it wouldn't help you. So it's going to be very dependent on your experience with language. And if we had more time, there's all the variation of it where I can put up low-frequency words, and it's much harder, of course, if you don't know those words. Now, so what Nick Chater and I are suggesting is that in order for us to deal with the immediacy of language processing, this pressure from the now and never bottleneck, what our language system engages in what we have called chunk and pass processing. That what we do is we chunk the language input together as quickly as we can into units and then pass it up to higher levels of linguistic representation. So just like you could chunk the letters here into the 3 words and maintain those for sort of recall. And it also means that what our language system has to do is engage in incremental processing. We have to process things as quickly as we can before the trace disappears. And we want to chunk information as quickly as we can. And what that means, we get representational locality primarily. And this can explain some effects in the psycholinguistic literature, such as garden paths effect and so on, if you're interested in those kind of things. Now, this picture also suggests that as you're chunking it together, passing it up to a higher level of representation, this actually gives us a natural way of explaining why it is when we think about language, we tend to divide it up into various levels of representation, such as phonology, such as words or morphology or syntax and discourse level of representation. From this perspective, this is because of the need to deal with the immediacy of language processing, that we chunk it into these different levels, and it just happens to be sort of fall naturally at different levels. Now, it may be different from language to language. So there are some languages where you might have different levels you want to chunk it into because that might work better for those languages. So languages such as Turkish, for example, you don't want to do words per se, but rather you want to do it at morphemes. You want morphemes combinations rather than word combinations that would be useful in English, for example. Now, it also means that our language system has to engage in what's called predictive processing. So we have to use all the available information, not just from what we hear, but also our expectations from what we know about the other person, what we heard before, from then our real-world knowledge, to integrate that as quickly as possible in order to be able to process things accurately and be right first time, because we can't really go back. Because once we have processed it, and that information will be gone. We cannot go back and sort of replay it in our head. Just like if you didn't listen to what I just said, you can't go back later and, well, actually you can maybe, but under normal circumstances, you can't do that. And if you're a child or if you're a language learner, right, the same applies there too. If you don't learn from the information as it's there, you cannot go back unless there's a recording. So let me give you sort of a cartoon version of how this might work. So we have sort of some auditory input, and we have time across here, and then of course there's some point in time that's now. That's where you're processing things right now. And what might happen initially is that the input get chunked into, say, phonemes. Now, in the psychological literature, there's a lot of discussion whether phonemes are real or not, whether it should be syllables and otherwise. Now, from our theory, we don't care either way. So if you like phonemes, it can be phonemes. If you don't like phonemes, you prefer syllables, that's fine. It doesn't matter. The purpose, from the viewpoint of this theory, what matters is that there's a sound-based unit that you chunk the acoustic information into initially. And what happens then, that'll buy you a little time, but then there can be interference between these phonemes when you have, say they're chunked into phonemes. Once you have a number of phonemes, you can start getting interference between them. It's a basic memory phenomena. So what you want to do is you want to chunk it together again into a higher level unit. That can be morphemes, that can be words or word chunks, which I'll focus on today. And then you can pass it up to the higher levels of representation, up to discourse level of representation. Now, I should mention here that these sort of levels here are purely for illustrative purposes. This does not mean that this is only the levels there. There could be many different levels. And in fact, different languages, as I mentioned before, might have different ways of carving up how you do chunking most efficiently. Now, this is sort of comprehension going from the input to some sort of understanding of what's being said on the one hand. But what we're also suggesting is that when we're doing production, when we are using language, we're sort of going through the same kind of process, but roughly in reverse, where we start with something like representation of what we want to say, the message. That's turned into intonational phrases, into words, sounds, and into articulatory gestures that are moving our articulators around. And it's sort of similar to what goes on in motor planning as well. Now, importantly, what I've talked about so far is about processing, how we process language in the here and now. But importantly, the now and never bottleneck not only has implications for processing, but also for acquisition and language learning more generally, because each processing event is essentially an opportunity to learn about the language and how to process it. So from this perspective, what this means is that what language acquisition is simply how to become better and better at processing language, doing this kind of chunk and pass processing. So rather than thinking about language or language learner as like a mini linguist having to identify the right grammar, what language acquisition is to become better at using language. So in particular, we see language acquisition as skill learning, that the child must learn how to create and integrate the right chunks rapidly before the input is gone. So the main pressure here is not about trying to identify this abstract grammar out there in some platonic heaven, but really to become better and better at dealing with the onslaught of input as it comes at us at a very rapid rate. And what this means is that what the child must do is engage in eager learning. It must learn as much as it can from the input when it's available in the here and now, and use all sort of different information, not just say syntax, but all the kind of information that's available at any point in time. Things like prosody, things like phonological cues to lexical categories, etc., and so on. It also means that learning will be largely local, sort of within the window available in sort of within a chunking window, and that means that abstractions that are made over are also likely to be very local in nature and build up in that way. And then, of course, the child has to engage in predictive learning, again, trying to anticipate what is going on and gradually learn to apply top-down knowledge from real-world knowledge, from discourse expectations and so on, in order to facilitate processing by way of prediction. And this perspective also allows us to go beyond acquisition to also think about language evolution. So because each language learner, of course, is part of a community of language users that drive the cultural evolution of language across time, although I won't be talking about that today. So just to give you a quick recap here, what I talked about so far, that what we are facing when we are communicating with each other by way of language is the now and never bottleneck, this extreme pressure on our language system. And the way our language system has to get around that is by way of chunk and parse processing. And what this means is that language acquisition and language learning more generally essentially involves learning how to become better and better at chunk and parse processing. And that from the viewpoint of language evolution, that constraints on how we do chunking more generally, there's some basic memory processes, are amplified by cultural evolution, can shape linguistic structure. And we've done some experiments that kind of to demonstrate that in the lab as well, but that's for another day. Now, at the syntactic level, this idea highlights the importance of multi-word combinations and multi-word chunks in language learning and use, and that's what I'll focus on in the rest of the talk today. So the question I want to turn to now is that how might chunking play a role in language acquisition? And by this I mean first language acquisition. And with a former graduate student of mine, Stuart Macaulay, we have explored this by way of computational modeling as well as behavioral experimentation. So first what I'll talk a little bit about is how we created a computational model in order to sort of demonstrate how chunking can actually lead to language-like behavior. So we created a model of language acquisition, what we call a chunk-based learner, or CBL, and we created that with a number of important psychological and computational features in mind. So we wanted to create a system that could model what a child might actually do. And in particular, what I'm going to show you data from is actually modeling individual children. So what we use is a database of so-called child-directed speech. So this is a large database of a lot of recordings of caregivers interacting with small children. Now, what we've done that's fairly unique is actually model each individual child separately. So we take whatever parents or caregivers are producing to a particular child and modeling that as input. Now, we also want to model, create a model that does both language comprehension or aspects of language comprehension as well as language production. Now, again, in a very limited form. So for those of you who are not familiar with computational modeling, of course, there's a lot of things you have that these models can't do, semantics being one of them. But what we want to try to show is that how very simple processes can account for interesting aspects of early language acquisition. And in particular, what we did was we took input to a particular child and then gave that to the model. And then in these corpora, what you have is that at some point the child will say something. So when we come up to a point when a child said something, it's then the task of the model, given what it's learned so far, to recreate the utterance that the child produced. So that's how we did the modeling. Now the model that we have was sort of built with the now and never bottleneck in mind. And in particular, we wanted it to do online processing. So many models that are out there rely on very complex kind of computational procedures with loads of memory and so on that is unrealistic from sort of a human infant's perspective. So we wanted to avoid that and instead have a model that only does online processing, dealing with things in the here and now. Incremental learning can only rely on what it's seen so far. It relies on local dependencies, and it relies on a very simple kind of statistical learning that we know from various kinds of experiments that young infants as young as 7 months of age are able to do. Very simple kind of statistics. It's item-based in the spirit of the work of Michael Tomasello. The model incorporates prediction. It builds up what we call a chunkatory. Now, a chunkatory is essentially an inventory of chunks. Now, these chunks can be single words or they can be word combinations. And so here there's no separation of grammar and lexicon in this model. What we have instead is a chunkatory that has both words and as well as these multi-word units. Now the model does both aspects of comprehension and production, as I mentioned, and it gets naturalistic input from actual, recorded, this is transcribed, but sort of interactions with real adults and children. And it also has substantial cross-linguistic coverage. So let me give you a quick idea of how the model works. So imagine that the child hears a simple sentence, simple transitive sentence, such as the cat chased the dog. Now, from the viewpoint of understanding language, what we want to do is having the model being able to essentially chunk this utterance into units that would be useful for further semantic interpretation, sort of passing it up for further semantic interpretation. And in this case here, what we want to do is to pass it in what's referred to as shallow passing into essentially the two noun phrases, the cat, the dog, as well as the verb chase in this case here. And the way it does that is by computing what's called backwards transitional probabilities. And that it's a very simple measure. And as I mentioned before, it's something that infants can do. Essentially, it's, if we take the two first words, it's the frequency of cat divided by the frequency of the last word here. So it's fairly straightforward. That's backwards transitional probabilities. And so essentially what the model is doing is that when it comes across a word, say there, and then it doesn't do anything, it gets cat, then what it looks at, it keeps track of the average backwards transition probabilities of what it's sort of seen so far in its input. And if if the current measure goes below the average, then it inserts a boundary. So if the average transition probability, backward transition probability here goes below the mean, then we insert a boundary between these two words here. In this case here, let's say for the sake of argument that nothing happens, so it gets the next word in here, and it does the same. Now in this case here, the boundary will drop, and the model will insert a boundary. It'll take what it has, this chunk that is separated out, it'll add it to the chunkatory with a frequency of 1, and then it'll pass it up for further processing, essentially. And then it goes on processing the next. And so we get to there. Ideally, it would insert a boundary here. It would add chase to its chunkatory with a frequency of 1 and pass it up for further processing, and then continue processing. Now, in this case here, you can see when we have it segments out the dog here, it already has this noun phrase in its chunkatory with a frequency of 2. So what it does is it simply increments the frequency by 1. So it keeps track of the frequency of the chunks as they occur in the input. And then it'll pass it up for further processing. Now, we wanted to compare different variations of this model. So we have our primary model here. We have a model that uses forward transition probabilities, which is essentially very close to the other measure, but instead of taking the last word of 2, you take the first word. That's forward transition probabilities. And then we have two other kinds of models. These are what's so-called trigram models. These are from computational linguistics, and they actually, essentially what they do is just you keep a record of all the trigrams, that is consecutive strings of 3 words that you come across in a corpus. Now, this may seem like a very simple model, but it actually turns out that these are very powerful model in the computational linguistics literature. They can go through, they've been used to, for example, model important aspects of the Wall Street Journal corpus, and they can do really, really well, actually. It's hard to do better than these kind of models here. I mean, you can these days, but you typically have to build a lot more in. So these models are actually very good at dealing with language generally, even though they're really simple. Now, when we measure comprehension, or this aspect of comprehension, one way is we could see, sort of the classic one where you have a complex tree. However, when you actually look at how people process language, people don't do this. they don't seem, there's very little evidence in terms of how people actually process language for indicating that they actually build these trees in their heads. So for example, if you look at how people are reading newspaper text, the best predictor of where their eyes are moving across the text is not captured by something like this, but actually something that's much flatter, sort of keeping more track of sequential structure. And indeed, also when we look at children, how they're processing language, they appear to do something much more like this, like shallow parsing. So this is the kind of thing we're going to compare with. So what we've done is we're taking so-called shallow parsers from the computational science literature. So these are sort of systems that other people have built. Now, these systems are actually quite complex in and by themselves. They have all sort of information that our model doesn't have. Things like lexical categories, like that dog is a noun, that there is a determiner, and chase is a verb. And so our model doesn't know anything about lexical categories. But nonetheless, we use that as our gold standard. Now, this is the performance of our model here. So this is averaged over 43 individual children that we model separately. And you can see here that the CPL outperforms the other models here and actually does quite well. So this is in terms of chunking it into the kind of units that we think are relevant for comprehension. As I mentioned, we also do this cross-linguistically, so the model also does quite well for German and French, where we could find a way of doing this. But what about production? Well, as I mentioned, when the model goes through, and so we essentially, because we are modeling children, we're modeling the input to children, but when the children say something, we want to model what they say. And the way we do that is in a very simple way. So say again that the child wants to express this, this utterance, the cat chased the dog. What we do is we use what's a so-called bag of word method. So we sort of kind of put it in a bag, and then what the model has to do is use what it's learned so far to essentially take these words that it doesn't know the order of it or anything, and then reorder them given the chunks it has in its chunkatory and what it's learned in terms of statistics to see if it can recreate the utterance. So essentially, ideally, what would come out is something like the cat chased the dog. Now, crucially, so what we use here as the gold standard, and what counts as correct here, is essentially what the child actually said. Now, if the model output, for example, the dog chased the cat, that's a perfectly good sentence in English. However, that would get a 0 because that's not actually what the child said. So it's a quite conservative measure. But even so, and even without any semantics, this is really about just linearizations of an utterance given the words. You can see the models actually does quite well here relative to the other one. Now, clearly there's much room for improvement here, but that's what semantics and so on is for, of course, that typically when we are expressing ourselves, we have something to say that's driven by semantics. Now, the nice thing about this way of modeling production is that we can actually model productions of children from any language that we have a corpus of. So indeed, we model children from 29 Old World languages, covering 9 language families and 15 language genera, and 4 different word orders, subject, verb, object, SOV, VSO, and no determinant order. So quite a spread of languages. And what you see here is a rather busy graph, but that essentially the models perform where we take the graphs you saw before, but overlay them on top of one another. So when you see green sticking out here at the end, that means that the CPL model performed best. So out of the 29 different languages, what we model here are 217 individual children. And the model performs better than the other models in 26 out of the 29 languages, so pretty good performance. So where it doesn't do better is for Russian and Romanian and for Korean, as you can see here. Now, interestingly, there was actually no effect of word order, so it didn't matter what the word order was. The model would do equally well on all of that. But let me sum up here. What this model suggests, at least initially, is that language acquisition, at least aspects of it, at the utterance level, can be captured by a simple chunk-based model using incremental online learning. And importantly, we also have variations of the model that learns from lexical categories rather than actual words, but it doesn't do nearly as well. So what this means is actually learning from words and word combination is much more useful, at least for children's acquisition, than it is learning from, say, noun for combination of nouns and verbs. That doesn't seem to help. It has broad cross-linguistic coverage. We also applied it to model data from various kinds of developmental psycholinguistic experiments from children that it can model quite nicely. It also has sort of the kind of classic comprehension production asymmetry that we see in child language acquisition, where children can generally comprehend much more than they can produce, which is a general sort of feature of language, I suppose. Now, very nicely, there was a recent paper that came out where some other people have taken the same model and shown that it actually can discover psychologically valid chunks that are reflected both in the age at which that you acquire certain words and also in the adult reaction time to certain words. So they kind of suggest that what the model does in terms of discovering these chunks is actually discovering chunks that are psychologically valid. Now, importantly, this model here, there's no grammar. What it does, it becomes better at processing language, becomes better at picking up these chunks, using them for comprehension and for production. So that's an important point. There's no separation of acquisition and processing and no separation of lexicon and grammar. They're sort of part and parcel of the same thing. The idea is that language is essentially, language acquisition is skill learning. But what about second language learning? We tried to do sort of some very, very preliminary work, try to see whether multi-word chunks may be important or how it might play a role in second language learning. So the simulations that we've done so far suggest that it may be very important for first language acquisition, but what about second language learning? So we looked at this in context of learning using the model in this case, in context of learning a second language, either German or English, by individuals whose native language was Italian. So the way we did this was that we wanted to sort of ask the question whether L1 and L2 learners use chunks differently. And in particular, we wanted to focus on the production they produce to see, are their ability to produce utterances better explained in terms of chunks when you compare L1 and L2 learners. And the way we did that, we used our CPL model, and then we used that to essentially assess these productions by L2 learners, whether they were more or less chunked than what we see in native speakers, either adults or children. And the way we did that is that we used a model. The model was trained a little bit differently than what I just told you. It was only trained on the actual productions that people produce, because that's all we had from the second language learning corpora. And in doing so, we essentially trained the model of 90% of the corpus, left 10% out, and see how well can a model that's trained on the production of 90% of the production that somebody had produced to the remaining 10%. And you sort of keep on swapping it out so you cover the whole corpus. This is referred to as a leave 10% out method. Now, what we were expecting to see is that L1 production should be better captured by the model than L2 productions. And so here the data related to L1 and L2 learning of English. So what we had here were several native Italian speakers that had been learning English. This is from a corpus of L2 learners by the European Science Foundation Second Language Data Bank, or Feldvik, 1992. So we have Andrea, Lavina, Santo, and Vito. And we compare that with L1 learners where we match the corpora in important ways in terms of complexity and utterance length as best as we could and so on. And what we had, so we had L1 learners. So we had these kids here, Connor, Emma, Michelle, and Emily. And then we had so these are of course native language learners, children. And then we have as adult native language speakers, we essentially have the parents to these children. And then, as I mentioned, you were matched for corpus size and vocabulary size and so on.
Why did you think the L1 learners would follow the model better than the L2 learners?
Well, so the model, because of the relative success of the model in modeling the child language acquisition, we believe that the model is capturing something fundamental about how first language learners learn their language. And we have some reason to suggest from work from, for example, people like Nick Ellis and others, that second language learners may chunk differently because they might, for example, apply their native chunking skills to the second language, and that might lead to some differences in how they do it. That's one possibility. So here are the results. So what you have here, we sort of divided up into, in the dark blue, we have the child L1 speaker, and then we have their parents L1, and then the adult L2. So we matched them very carefully, these corpora. So we have Connor, that was the child, and then Andrea, that's the L2 speaker. So here we have Andrea, here we have the child, here we have the adult in the middle. And you can see in all cases, except here, for Vito, we have that, so here actually the adult L2 learner is not doing as well in terms of chunking as here. But what this suggests is that these L2 speakers, their output, their productions are less well captured by this model than are the L1 and L2, are the L1 child and adult. We did something similar for German. So here we had, again, native Italian speakers learning German. So we had Marcello, Angelina, and Tino. And then we had matched corpora Laura, Nancy, and Leo that were native German learning children. And then their parents. And then again, we matched the corpora for size and so on. And here are the German results. Again, we see something very similar, that the adult L2 speakers, that their ability to produce sentences are not captured as well by the way the chunk model works compared to the children and the adults in this case. So what this suggests is that the L2 speakers' productions are less chunked, or at least knowing the chunkiness of certain utterances doesn't generalize to other kind of utterances, whereas it does for both the L1 adults and the L1 children in this case. We also quickly wanted to compare it with the original CPL model, the one that I talked about in the first case, and this is what you see here in green. And what you can see, so this is models that are trained up on the parental input and then tested on the child's production in this case. And what we can see here is that that's still doing, there's doing comparable here. This is the child in the trained only on productions, and here we have the L2 speakers here. This is average across all across the two different languages, German and English. Now, this of course is very preliminary, but what it does suggest, and we have some additional analysis where we instead of we want to try to look at might there be a way of changing the model that might better capture the L2 learners, the way they're doing chunking. And one way we did that, where we did get some improvement, was instead of using transition probabilities, we're just using raw frequency of the chunks. That actually seemed to be counting better, indicating that perhaps, and this is also following a suggestion by Nick Ellis, that L2 learners, they will be trying to apply chunks, but they may be driven more by raw frequency rather than probabilistic relationships between words in between them. So what the results suggest is that there might be some differences in chunk use between L1 and L2 learners. And we've seen both in the modeling, and there's also a growing body of work, empirical work with various kinds of behavioral studies showing that kids and adults use these multi-word chunks as building blocks for their language performance. And we know that it remains important for adult speakers, which I'll also show to you in just a minute. But also there is a suggestion that L1 and L2 learners may use chunk differently. And that's perhaps something we can return to during questions and discussion, I hope. But I want to conclude here with sort of a way by underscoring just how important these multi-word chunks are in terms of our language ability as native speakers. Although I'm not a native speaker, but those of you who are native speakers of English, that would be applied to you. Or of any language, for example. So the model and other work suggests that these multi-word chunks are important for language acquisition and processing. But what's their representational status? How are they sort of stored in our minds, as it were? In particular, I, along with others, have suggested that these multi-word chunks are actually key building blocks of language acquisition and adult language use. The question is, are these chunks stored as such in a way that's suggested by the model, or are they sort of generated on the fly by sort of combining words as we're using them more generally? Now, one way of approaching that is that when it comes to thinking about the representational status of multi-word chunks, sort of idioms often comes to mind. So the thing about idioms is that you really need to store that as a unit in order to be able to figure out what it means. So if you have sort of expressions such as, you know, to kick the bucket or spill the beans or let the cat out of the bag, in order to get to the intended meaning of those multi-word constructions, you really need to have them as a unit, because each of the word in combination will not tell you what that actually means. And of course, that's one of the things that's often a challenge for second language learners, is that I certainly found that in many cases that what works as an idiom in Danish doesn't necessarily work as an idiom in English, and so on, and vice versa, of course, something I'm sure we all have experienced. So the suggestion is, and there's a fair amount of work on this, is that idiom meaning may be compositionally opaque, meaning that kick the bucket, the fact that you know what kick is and bucket mean will not tell you that it actually means to die necessarily. And indeed, it's been suggested that they're stored as a single unit in one way or another. Although not necessarily as a unit that's undifferentiated. There's some interesting data suggesting that you can actually prime the individual words too, but more perhaps like a unit that's a sequence that you stored as such. As it would be, for example, in this chunkatory that I talked about. Now, previous work have shown that there's a processing advantage for idioms. So if you give people so-called self-paced reading task in which you read sort of one word at a time, what people have found is that when you have an idiom such as hit the nail on the head, that's processed faster than sort of a comparable expression, hit his head on the nail, for example. And also, if you use eye tracking, it's been shown that at the end of the day, it's processed faster than at the end of the day, even when you try to control for a number of things. However, there are some limitations with these studies. First of all, that they generally don't control for how meaningful the foil is in this case here. They also don't control very carefully for the frequency of the individual words. So what my colleagues and I wanted to do was to ask the questions, do idioms really have a special representational status? Or are they just idioms and conversational multi-word chunks simply two kinds of constructions, two kind of chunks that we have, such that idioms are not really special, but rather multi-word conversational multi-word chunks are stored also at these units, as I would be suggesting. That is, that they would be essentially conventionalized for meaning mappings at the multi-word level. So what we wanted to do was to carry out an experiment in which we tested this fairly directly by comparing idioms and highly meaningful conversational sequences, and our expectation was that they should be processed very similarly. And then we also expected that what would matter is more, even overriding frequency, would be how meaningful these units were. And so what we did was we carried out a so-called phrasal decision time study. And essentially, it's a study in which you would sit in front of a computer, you see in this case, a 3-word chunk, and what you have to decide, yes or no, would this make a good sort of subsequence of a sentence of English, yes or no. It's modeled on a basic task called lexical decision task that's been used in literally thousands of experiments to understand sort of the nature of our vocabulary and so on. Just this is sort of the multi-word version. What we did was we took a number of idioms from 2 idiom dictionaries. We had comparable conversational phrases, and then we had fragments. Now, importantly, we controlled for the frequency, for the overall frequency of the 3-word combination, but also for the frequency of the first 2-word combination, play there, and the second one, the field, as well as the frequency of the individual words. So this required doing a lot of computation in order to find stimuli that would work in this case. So these are all matched for frequency across, in this case here. And we use just using sort of corpora of American English around that incorporate about nearly 40 million words of American English. Now, before we could really get to sort of actually the processing bit, we needed to first control a number of things. We wanted to make sure that all the 3-word combinations were equally plausible as part of an English sentence. So we first carry out one norming study in which we ask a lot of our undergraduates here at Cornell whether this 3-word combination was a plausible sequence as part of an English sentence. And as you can see here, all of them were considered to be very plausible sort of 3-word sequences. We also wanted to make sure that the idioms and the phrases were equally meaningful and more meaningful than the fragments. Now, the fragments, I should mention, sort of kind of straddle a phrasal boundary. That's why they're fragments. So what we did, we carried out another norming study in which we asked another group of undergraduates to rate how meaningful these 3-word combinations were as part of potential part of an English sentence. And you can see both the idioms and the phrases are considered equally meaningful and more so than the fragments. And then lastly, we wanted to make sure that the idioms were actually considered to be idioms, that they were sort of read as idioms. So we had yet another group of undergraduates rate our items for idiomaticity. And you can see the idioms were rated as more idiomatic than the phrases, which in terms were slightly more idiomatic than the fragments, as we want. So with all that in mind, we could now get to actually test whether the idioms and phrases would be processed equally fast. And indeed, what you see here is reaction time measured in milliseconds. And you can see here there's no difference between idioms and phrases in terms of how quickly people can process them. And they're processed much faster than the fragments in this case here. So what this suggests is that that both are likely processed in the same way, or at least there's no difference that we can ascertain in reaction time. So to recap, one of the things that we found in our statistical analysis is that one of the key predictors of how quickly you would respond to it is how meaningful it was in our norming. And that meaningful compositional chunks appear to be processed similarly to idiomatic phrases, indicating that both of them are stored as a unit as such, or a sequence of words in a similar way. So if idioms are stored as a unit, which makes sense given the examples I gave earlier, then what this would suggest is that that equally similar but non-idiomatic three-word combinations are also stored as unit in a way suggested by the model. And then lastly, this we take as suggesting that similar mechanisms are used to represent both idioms and meaningful multi-word chunks. So in conclusion, so first of all, I started out by arguing that we should reintegrate the language sciences and all work together to really understand how language works, not in separate departments, but actually have integrated departments of language science. And I just, a few weeks ago, I gave a talk at Penn State, and they have a language sciences center there. It was great. So it turned out there was many people that were in the Spanish department actually doing similar work to what I do. And it was a wonderful opportunity to talk with people working with second language learning and so on, doing research in it, as well as also teaching. And so it was kind of a nice model for how one can begin to integrate the language sciences. In terms of content, what I talked about is that our language system is facing this now and never bottleneck. And in order to get around that, what our language system does is engaged in this chunk and parse processing. And that as a result of that, we see that multi-word units are building blocks not only of acquisition, but also of processing. And there are some suggestions, both in the work I presented here, but also in other people's work, that there might be different chunk use in second language learning. And there's one of the things that came out of my visit to Penn State was some possible collaborations looking at a way that we've developed here to measure chunking ability at different levels of representation as a way of perhaps assessing the proficiency in a second language in a way that may be easier than other tasks. And I'm also working with a graduate student in information science, actually doing that online right now. And we have some preliminary results that are very, very promising that I'll be happy to talk a little bit more about. But on the theoretical level, what this perspective suggests is that this old classic view of separating out grammar and the lexicon maybe is not the right way of looking at, but rather what we have instead is an integrated system that involves essentially becoming better and better at processing, such that language acquisition is not something that just happens until puberty and then language processing takes over, but rather what language acquisition consists in is just becoming better and better at processing language. It also suggests that everything else equal, that perhaps the processes involved in language acquisition may not be that different from what's involved in second language learning, although of course there'll be a lot of differences in where in their lives and so on people are when they're learning a second language. So with that in mind, I want to acknowledge my collaborators on this, my longtime collaborator Nick Chater from University of Warwick, Stuart McCauley, who was a graduate student with me, who's now at the University of Liverpool, Heinal Jolschwei, who was a postdoc with me, funding from the Binational Science Foundation, and thank you to all of you. Here's just some frivolous advertising for my recent book, Creating Language. Thank you.
So it seems to me that one reason a second language learner wouldn't be as predictable a chunker is because that individual is trying to is not so much present in the immediate input as a first language learner child is. That language learner has got all sorts of other things he or she's thinking about, and maybe trying to process into this environment where the second language is going on. So would that mean that in in learning to, if our goal is to get our students to chunk more efficiently in this new code, would we want to kind of tightly direct and control and maybe limit the the input and word environment that the learner's working in, as opposed to letting the learner talk about something that the learner's never had any input about, for example. To stay on a set of topics which we've introduced in class and that the learner has had a lot of input in. Talk about what you've heard, not something from the rest of your life. So one of the threads in language learning is, oh, tell me about yourself. Tell me about your family. Well, to some extent, if we've already talked about, I had a lot of input about families, and the learner can fit into that, maybe that fits more similar to language learning and more similar to efficient chunking. But if the learner then goes off into something else entirely that's maybe important to that person, maybe it's all about migration in that person's mind, the family. But we haven't talked about that, and the learner has no input about that. That's not as efficient a way to do it, and maybe not what we want to try to do in learning, and maybe responsible for why your predictability scores are lower with second language learners. Does that all make sense to you, or what do you think?
It does. I mean, I think there's a lot of interesting question there. I mean, you're completely right that oftentimes when you're learning a second language, there's all sort of other things going on in your life. Whereas a 2-year-old learning language, that's one of the main things they're doing, right? So if you're learning a second language at Cornell, that's all sort of you have other things you're doing at the same time, and that's going to take up your time and your mental energy and so on. But on the flip side, that's clearly the case, that the state of the learner in that regard is going to be different in important ways. But it also, this perspective suggests, at least a possible explanation why language immersion generally appears to work quite well when people are, able to be immersed in the right kind of way. That having that exposure to the L2 would be helpful in sort of building up better chunking abilities. Now, one of the things that's going to happen, depending on the nature of the L1, is that whatever chunking that they have used in their L1 will sort of potentially bleed into how they might do the L2, and sort of kind of overriding that in the right kind of way can be important, and doing that at multiple levels. And there might be, I mean, I haven't done any work on this, but I could imagine that there might be some way of teaching chunking skills in the second language that might be able to make it easier for them to make the right kind of chunks. And that could be perhaps even by having some very curated kinds of samples that they're exposed to that would be highly representative of sort of the main kind of combinations at the different levels they might be exposed to. Now that would be kind of potentially really boring to do that. But one of the things that I'm doing with the graduate student from information science is actually having people watch movies. So one of the things, you can do that on a computer, and there's all sort of really cool things you can get the computers to do these days, including translations on the fly and so on. And one of the things we are trying to do is just having people, when they're listening, they're watching a movie, say, and then every now and then they just have to repeat back one of the utterances that they've heard. So one of the things that helps on this account is that helps this chunking ability if you have to repeat it back. So actually the act of having to repeat it back forces you to represent it in a way that's important rather than just listening. And we have some preliminary data from a task where their ability to repeat back is really highly predictive of their ability to actually take an utterance and translate it correctly. So this is not really, this is just a way of measuring how good they are, but the idea is that if we can improve their chunking skills in some way by exposure, we might be able to also improve their language skill more generally. Exactly how to do that is an interesting question. That's one of the things that I've been talking with the folks at Penn State about maybe investigating. And there's a couple of graduate students there that we talked about doing a project next year on that. So that would be Spanish and English primarily. So I think there's some possibilities there. There's still a lot we don't know, and whether it will work or not, I don't know. But there certainly in the past there has been, to my knowledge at least, I think it's the Pimsleur method or something, where you actually cheat people sort of some chunks already. And there's some also remember visiting UCLA, talking to John Schulman there about how he would essentially teach sort of individuals about like 1,000 sort of chunks, and then they could go out and use those, that they could actually get by to a certain degree. Now, they wasn't necessarily done in exactly the way that I talked about here, but I think there's a little, if one looks around in the literature, there's some few pieces of evidence that suggest that maybe if one thought about this, or if one could sort of approach it in a more general way, that it might be possible to do something like that. I mean, we know we're very, I mean, one of the things that humans are really, really good at in general is pattern recognition. And this is sort of what this is. And if we sort of focus people's attention on that rather than on other things. Now, that doesn't mean that we don't want to have them talk about what actually they care about, because that's the other part of it. We still want them to actually learn, to come back and learn something, right? So there's going to be a trade-off between having something that will motivate them to learn and come back to learn more, as well as sort of trying to maybe hone some skills that would be important in improving their ability, but that may not be sort of obvious at first. But that would be, a potential implication. But having not done any sort of direct experiments on that, I don't know whether it would work, but that's an interesting prediction. So I think there's a lot of interesting things one can do in that regard.
I remember working with a student in English who has dyslexia, and we were going over his writing, and he said the words would just fall out, as he was going through. So I'm wondering if you had worked with students that were folks with that situation, or whether this chunking could help in that situation. So
I actually put in a grant proposal for how to apply some of these ideas to learning how to read better, or to measure different individual differences in reading skills. And one of the things we know about reading sort of in general is that one of the best predictors of people who have reading problems is actually what's referred to as non-word repetition. What non-word repetition is essentially a kind of chunking. And with my graduate students too, we actually created a better way of measuring that was more predictive of how well kids would read in first grade, at least in some preliminary analysis, than the standard form. So there are ways in which one might produce that. And there are ways in which there's some old work going back to maybe the 70s or so on, where people actually also looked at chunking text in a similar kind of way. And that seemed to facilitate sort of reading understanding to some degree. It wasn't very much, and for some reason it never took off, but it might have been because it wasn't done in the right way, or just that the field was focusing on something else. But there certainly is some ways in which that maybe these kind of skills, or sort of emphasizing them in the right kind of way, might help. But again, not having done the proper research on it, but I think it might work, yes. But I don't know that for a fact. Yeah?
What about at the level of super-segmental? Has anyone does that at Penn State? Like how you chunk it into the pronunciation at super-segmental, so that you will sound more like a native. That's the pronunciation.
Yeah, I think so. So that's a good point. In fact, so one of the things we were playing around with the student from information science was actually trying to have people repeat back sort of watching a TV show. So some of the TV shows were in, say, in Japanese or in others. So the nice thing is that the kind of system he developed, he could do it in any language where there were essentially like a Google translator on. I mean, clearly Google Translate will give you a lot of rubbish. But the idea is that if you can have people, when they're watching something, every now and then the video will stop and they have to repeat back like an utterance. And the idea is you can get people to do that sort of more generally, sort of having them to do more of the production. I mean, oftentimes, at least this is how I was taught second languages, you don't end up talking as much as would be useful because a lot of it is by way of reading. And reading, of course, is a good way of building up vocabulary and so on, but also actually having the actual interaction with actually producing the sound and repeating that. And that's where a computer system can come in maybe and help us so that, you know, we're not going to be in a world where, you know, each language teacher will just get 2 students and so on, right? It would be nice if that was the case and we could sort of work like that. But most of the time, that's not what the society is willing to pay for. But if we can have some computer systems that in some way can take what you're saying and help by analyzing it, sort of help you improve pronunciation at some level, there's still going to be interference, right? So even people who have spoken a language for a very long time, so like me, I've spoken English for a long time, I still have an accent when I speak English. And that's true for most of us who are second language learners. But nonetheless, by keep on doing it and over again, you know, practice does not make perfect, but it does make better.
It's like a chunking the lexicon is one thing, and then also chunking the pronunciation.
Right, across multiple chunks, yes. And so in fact, there's some nice studies indicating that when you have these chunks in actual speech, what you see is that the chunks themselves are actually reduced in faster duration. So we know from, at least for this is from L1 learners, that if you can get that in as a chunk, you might be able to get also the pronunciation right. But of course, there are also cases where you have, you know, the stress patterns that go across the whole sentence that can be hard. That's a different ball game to try to catch. That's hard.
I was thinking of like Indonesian is all heavily morphological aspect of it, and then you can put them into phrases and chunk them. But then when they say it, it doesn't sound like you know what I mean. That's another level.
Right. I mean, there's certainly
So
so there's different levels of proficiency, and some of it might be hard to get to the fully native ability. So I mean, there are I don't know anything about Indonesian, but I've looked a little bit on at Turkish.
Are they doing that at Penn State? Like Jim Lantok, they're doing something?
The people I spoke was primarily focusing on Spanish. But there's also the Spanish department. But I've looked at, I mean, so for a variety of reasons, including theoretical reasons, languages like Turkish that are glutinal languages are interesting because they're, you know, a single word can express what you would use a full sentence for in English. But there also you find chunking just at the level of morphemes rather than at the level of words. So that's part of the area that for the different languages may have different ways of sort of carving up the chunking space. And it'll be important from the viewpoint of if one was to apply ideas along these lines to take the nature of the specific language into account, so that for something like Turkish, one would want to stress sort of multi-morphemic units, and there's some preliminary corpus analysis indicating that you do get these chunks at the morpheme level in Turkish, even though you also have more freedom to move things around in Turkish compared to what you can do in English. But there's still, you know, much to be done. But initially, one idea is that one way of helping people to get into the system would be to have them to increase their ability to keep chunks in memory. And that's part of what kids learn when they learn their first language is sort of increase what they can keep memory. And if we can sort of facilitate a similar kind of process in a second language, that might be a way of getting people to get to a higher proficiency quicker, perhaps. But of course, that would have to be specific to the actual languages. Now, that wouldn't deal with the getting closer to the native accent.
But I can see they can chant it, but then when they say it, the pronunciation is, so that's another one. That's what I was thinking.
Yes.
It's interesting, that level.
By far the most complex slide that you gave in this fascinating talk was the one with the 29 languages, and 26 of them had the CBL coming out on top, if I'm remembering right, but 3 didn't, Romanian, Russian, and Korean, if I recall correctly. But there was lots of other variation in that chart. It's kind of mind-bogglingly complex, I think, in that respect. Do you have any hypotheses, working hypotheses at this point as to what makes for that degree of, I mean, there's a lot of variation there in the findings of these different models. Is there something systematic? I would think there must be something systematically different about these languages that's creating this diversity.
So that's a very good observation. So some of the variation is not meaningful. I'm sorry to say. Some of it has to do with the size of the corpora. So when you do this kind of work, you're sort of hostage to what's available to you to work on. And some of the corpora are very small, meaning that the utterances that are produced are sort of undersampled, as it were. And that can lead to a lot of variation that are not meaningful. But there are some of the variation that are more meaningful. There is one result that we have that sort of suggests at least that's one thing that's not captured by the model. So, and that's the morphological richness of the language. So what we did was we sort of created a measure of morphological complexity. It's essentially the type token ratio. It's kind of essentially how many variations do we have of a particular word. And what you see is that you get sort of a list here from not very high, and then to more complex patterns here. And when we then look at across languages, we then get that there is actually an effect in the model that the more morphological rich a language is, the less well the model does on that. And that's because for the viewpoint of the model here, it's not able to use the internal structure of the word.
So this echoes the previous remark you made about the difference between morphologically complex languages that have words that are
So this is
a dozen morphemes in a row. Okay.
So for the viewpoint of the model, it's a word is just essentially like a symbol. But for one of the things we know from the study of, at least from first language acquisition of morphologically rich languages, is that even though you have languages like CELTAL where a verb has 400 different forms or something, kids learn that just fine, right? And they're able to generalize and so on. But part of it is that there is actually some nice patterns to it that are meaningful for understanding what is being said. And the model doesn't have access to that. So one of the things we are working on is trying to give the model access to that, and then hopefully we can make this go away. So part of this variation you saw in these corpora is due to this. But interestingly, we thought we would get an effect of word order. But we, as I showed, the graph I showed sort of previously, there's no effect of word orders. And the model doesn't, at this syntactic level, as it were, it has no problem, but it's not able to take advantage of the information there is in the morphologically rich languages. Now, of course, as a second language learner, we know that if you have to learn a language, right, you ideally don't want to have to learn languages towards this end, because it's really hard picking up on these complex morphological patterns as a second language learner compared to a first language learner. And certainly the model has a little bit of that too. So that's part of the explanation for that variation there, I think, is in there. Part of it is the size of the corpora, as I was mentioning. Part of it is the effect of morphological complexity.
If I can ask one other very different question. You said in one of your slides that as we move up the levels of linguistic representation, we're compressing. That was the word you used. There are exceptions to that, though. For example, when you move to the discourse level, I'm thinking of that cat that took a bite out of the apple and jumped onto the chair. You get what I'm doing? That is, I created a story about those three words that makes that sequence all the easier for me to remember, but not by compressing it. I, in fact, expanded it to include visual images and movement and so on. And yet, it's measurably going to be easier for me to remember that tomorrow, probably better than Dick would have been able to remember it tomorrow, because I created that story. So there are these non-compressive techniques that are well documented as ways of improving the memorability of something. So how does that relate to the claims you're making otherwise? Yeah.
So there's at least two sort of comments or responses I have. So on the one hand, so when you go up, so what we are suggesting, you do what we call lossy compression. So you're throwing out information, but what you're also doing at the same time is that you're enriching it with top-down information from the discourse structure. So in this case, what you end up with is a discourse representation that has all the kind of things you're talking about, including real-world knowledge and so on. So you end up with very rich representation, but it's not the veridical sort of acoustic stuff. So the idea is that you gradually throw away from things like the word order and other kinds of things, because what you ended up with is a richer semantic or discourse level representation. So I think that fits with your observation. It also fits with data. For example, there's a very nice study from some colleagues of mine at University of Aarhus in Denmark, where they took a story, so not unlike video, but it's a longer story, and people would read them, and then they would test afterwards how many sort of details they could remember of the story. And what they found was when you just read the story through in the right order, there was many details people couldn't remember, because what they got out was the overall meaning of the story. And that, of course, there's old experiments going back to the 1920s that show similar kind of this. Then they did another thing. They took the same story, they sort of reorganized phrases or sentences or phrases, and then helped people do it. Interestingly, what you found is that in those cases, people would actually remember more details simply because they didn't know what to do. So part of what you can get these task-specific effects when we, as researchers, do all sort of weird things to it. But under normal circumstances, when we're using language, we are trying to get to the meaning of it. We're trying to understand it, build some sort of representation of the full story, where in a sense the individual words don't matter as much, but it's the full story that matters.
And presumably the people reading the scrambled version would have more difficulty remembering the story as a whole.
Yeah,
right?
so they were remembering. So there you got all the details. So it's like you had the trees but not the forest. In the other case, you have the forest but you don't have the trees, so to speak, to use a metaphor, I suppose.
This is more an anecdote, but an interesting experience I had recently. I went to a defensive driving class, and they were testing us and showing us a unit on paying attention. And they put up a sentence quickly, like you did with the jet engine. And they said, count the number of F's. And we all said 6. And he said, wrong, there are 8. But we missed the V of.
Yeah.
We missed the 2 that were, it voiced?
I use that example in my class too.
Okay, so what's happening is my brain is thinking that my brain is going by sound, right? Thinking that F is like off, OFF is an F. But I completely missed the 2 ofs with F is V.
But there's also, depending on exactly what the passage was. So when I put it up in my psychology of language class, I actually get, oftentimes they count even less. So some of them have F's in the beginning of the words. Those are easy to see. Some of them have inside, so that one of the words is scientific. So people get that. But the ones off are the one people ignore. I mean, part of that is that when in skilled reading, we oftentimes jump over function words like of and so on. And so even when we are counting it, it's just an automatic way of reading it, because we take them in the periphery of the content words. And so that might be part of what happens in that case. So we don't always take.
For me, I'm really a sound music person, and I think it's because of the V.
It could. I mean, it could be. It could be part of it, but I think also generally just that function words is what we tend not to. Another thing is that you can ask people of coming up. If you ask people to come up with words that start with an F, it's easy, right? If you ask people to come up with a word that has an F at the end or something, or any letter, right? It's much harder, because that's not how we tend to store or access information like that. So it's one of these kind of nice examples that are playing trick on this. There's another example that sort of related to defensive driving, well, even worse than defensive driving, I suppose, is sort of also, but that's done similarly. So these were pilots sitting in a flight simulator, and sort of they were coming in to land. And of course, normally when you come into land, there will be no plane on the tarmac in front of you. But when they put in planes in front of them, oftentimes they didn't see it because they didn't expect it to be there. This is really scary. This is real. These are actual pilots in real sort of.
And also the plane can be right directly below you, so you may not be able to see it.
Well, no, it was visible. So in the same way as there's all sort of variations on this kind of task. There's a very nice one where you're watching sort of a natural, sort of like a scene with fields, and what happens very gradually is that the field is essentially mowed or something in front of you, but you don't notice it until maybe fairly late. And so it's only when you sort of happen to look at the right places, and there's a YouTube video of sort of people making fun of it, where they're sort of talking about stuff, and then they you see this camera angle and that camera angle and so on, you sit back and forth, and then you change their clothes and all sort of other things, and oftentimes people don't notice it, like suddenly the different color shirt or something else. I mean, we're really bad at this kind of information, which is scary.
Famous story of Harold Robbins' editor at Simon & Schuster. Harold Robbins was notorious for procrastinating on his writing, and he made millions he made a lot of money for them. So he sent in part 1 of a manuscript and spent his advance, and then they got on his case, and you have to write the rest of it. So like a year and a half later, they finally said, we're not going to give you any more money until
you want read it.
They said, we're not going to give you any more money until you finish this novel. So he kind of, was crabby and sat. They literally like locked him in a hotel room for about 4 to 6 weeks, and he cranked out the second half. And they get it at Simon & Schuster, and this is their big like superstar writer, makes all this money for them. And they look at part A and part B, and the names were different. Like it was Cheryl in part 1 and like Cindy in part 2. And Cheryl had blonde hair in the first part and brown hair in the second. But she had blue eyes in the second part and brown eyes in the second. So all these details didn't match. And so they went back to Harold Robbins and very diplomatically said, we noticed these discrepancies, and we'll fix it. Just tell us, do you want to go with the characters in part A or part B, and we'll basically knit it together. And he got really mad and said, forget it. He said, I've been doing all this work for my audience, doing all this work for years. He said, let them figure it out. So he refused to make any changes, and Simon & Schuster published it as is, and they didn't get one letter of complaint. They thought, the editor, Michael Korda, thought they were going to get all these letters, people screaming, what's wrong, and they didn't get one letter of complaint. But it was because Harold Robbins knew they weren't reading his work for, he knew his audience really well.
Right.
And they weren't.
They didn't pay attention.
Yeah, and he said, let them figure it out, and the audience did.
Huh. Wow.
But doesn't it one issue that I'm struggling with is the notion of comprehension as it's represented in this model. It seems to me that it's a very surface level, and people can parrot back chunks of language, and they can gain facility in doing that, and they can gain fluency, and that's certainly a part of language acquisition. But it seems like it's a little bit broad-reaching to think of that as comprehension, and especially if you're not including semantics, which to me is a little ironic in terms of the notion of integrative, right? So how do we make meaning? It's rather more complex in a certain sense, and especially when you get into second language learning, where you don't have
the schema for being able to interpret and really understand or comprehend something that you might think you understand, especially if you're working with cognates, right? So, but if those cognates have other meanings, then you're just going, and there are studies that show that first impression from the first language totally skews the comprehension, right? And that it's in fact very hard to undo those first impressions, that people will maintain those kinds of misunderstandings, let's say. So, I mean, I would love to see an overlapping of somehow of mapping of semantics somehow within this to give it a broader sense of language acquisition.
So, I mean, you're completely right. I mean, the model is not a full model of everything that goes. So it's essentially is one of the levels that I talked about in the sort of this cartoon version, and so it's meant to capture that. So that's why I oftentimes, when I give a variation in this talk, I do comprehension and production. So it's not meant to be true, complete comprehension. What it does, I think, show is how far you can get in capturing aspects of comprehension, or picking up on the kind of things that would be that are important for further comprehension. That's why I was sort of kind of saying that they'd be passing up for further comprehension. Now, one of the things some data that I think is interesting that you might not, that at least I didn't think the model would be able to capture, is something as complex as this task here. This is actually something I think. So one of the things I think is underappreciated, and that will be exploring with second language learners too, is just sentence repetition or sentence imitation as a way of measuring skill in both first and second language users. And so here you have this is a study done with I forget how old they were. These were. Let me see if I can see. I forget how old the kids were. Maybe I think they're about 5 years of age. But what this is essentially, you can see these are different sentences that all have relative clauses in them, and different. And one of the things that these sentences have been used in, there's something called the sort of relative clause hierarchy, the Keenan-Cumry. The Keenan-Cumry hierarchy of different languages, which they have this form, they have this form, and so on. Now, what these on Tomasello show with the kids is that what you get is that when the kids are using these sentences, you can see some of them they're really good at, and others they're not. And so these were 4.5-year-olds, and the hierarchy is the accessibility hierarchy, and you can see they're good at these simpler ones, and they have a hard time with the genitive version here. Now, here's the model. Now, remember, the model doesn't have semantics or anything, but the model actually models the data quite nicely apart from this one here. And this is without even having any kind of memory. They can model what the kids do in these. These are relative clauses is something that's generally considered to be a complex part of our language. So I think that's sort of interesting in and by itself. Now, that doesn't mean, of course, that there's no semantics in there. Of course, we actually have a version of the model that has a little bit of semantics in it that we're beginning to play around with. It's still a very simplified version of it, and nothing like what we have in people. Now, this is also what I was prefacing when I started talking about this, that when you do this kind of modeling, getting to semantics is really hard. Now, dealing with phonology, dealing with syntax is relatively simple by comparison, because you can just rely on the order of phonemes or the order of words, and so to some degree, or build other things in.
Semantics is complex.
It's hard, yeah. And also the problem is that it's hard to find ways of representing semantics that is not ad hoc. And so, in fact, my student and I, we have a paper, sort of a review paper, where the argument is that models of acquisition need to take semantics seriously. That's sort of the whole paper arguing that that's the next step. So we have a variation of the model that does have semantics that we are playing around with. We don't have much data on it, but it does learn sort of a nice context level of semantics. So, for example, if the word cat is experienced in a lot of chasing context, like in this talk here, for example, when the word cat is activated, you also get chase being activated at the same time in a way that would make sense. But it still doesn't build up sort of a discourse level representation. We can't do that yet. But in the
Beyond the binary, this is the thing with computational, you tend to get into binaries, right? So when you talk about semantics, you really have to get into a different sense of system of meaning making. So I think something like metaphor theory helps. As a language teacher, I find metaphor theory to even prototype theory, right? You work with prototypes that can then be extended to create have metaphorical extensions, start to create this schema of things, and you're working in a very different way of making meaning than what can be broken down into, let's say, more binary kind of relationships.
That's true. I mean, I wouldn't say this is binary because this is probabilistic, and that's a little bit different than it sort of binary tend to be categorical either or, but this is probabilistic.
Ultimately recognition as opposed to non-recognition, or ability to chunk, to give back a chunk as opposed to. I mean, isn't that the basis kind of
well, so that's the way the performance is measured, right? So that's a trick. We have to measure it in some way. So essentially here, what we are trying to do is, so how far? So so essentially the question we are addressing in the modeling part here is that if you have a model that picks up on chunks and the relation and statistical relationship between them, how much of the child's or linearization of utterances can you account for without semantics? That's not to say semantics is not important, but we can account for about 60% of it. Now, again, there's the other part that you clearly require semantics, as I said, and all sort of other things. So it's not to say by any means that semantics is not important. So the framework that I talked about sort of has semantics and discourse, and that's how we would account for the question that Stephen that Stephen asked about, the cat sitting on I can't remember. It's not the cat sat on the mat, but it was some other cat sentence that. Yes. And so that would be sort of in the discourse representation, and clearly the model doesn't have that, and clearly the modeling needs to go quite far. But it does, I think, shows at least initially the feasibility of if you pay attention to this chunk information, you can do that. You don't need to build up these trees and stuff like that. So it's also a way of showing that. So there's another approach which suggests that you need to build these very complex trees that I drew the red cross over in order to understand language acquisition. And I think that's wrong. I don't think there's any data that supports that necessarily. But that's an assumption that's very common in linguistics in particular, in certain aspects of psycholinguistics as well. And this is a way of saying, well, actually, if we can account for this data without these trees, right, or at least reasonably well, and this is without semantics, that if we had semantics, maybe this would go away and it would fit better. That does show, I think, at least as a first step, that there's something to this idea. And then we have then of course we have all these experiments we do with children where they have to do a variety of things, and there of course they're using their semantics and so on, and we can map that on to the model in this way. But you're of course right that semantics is important. I wouldn't want to say that because the model works in this way that semantics is not important or anything. That's why it's just aspects of it. It's sort of trying to say, if you're interested in the linearization of finding out what you can learn from sort of the order of words, do you need to have a tree structure built up inside in order to sort of get off the ground? And the answer, I think, is no. You can do it with simpler means. That doesn't mean that semantics and discourse and so on is not important. It's still going to be critically important, I think. It just happens to be that we're not able to model that.
Well, and you did hint earlier at the possibility that the difference between the L1 and the L2 data may reflect these same variables. That is, that the adult learner is bringing a raft of,
Oh, yeah.
of information about the way the world works and all sorts of things that can be called upon in this process and louse up what might otherwise be pretty good a match to your model because there are these other things imposing on it that the little kid doesn't have.
Exactly.